It's the end of the 19th century, and the scientific community is feeling pretty good about itself. There was this genuine feeling that, the great fundamental laws of nature had been discovered. All that was really left was to just iron out a few minor details.
Yeah, about that. Turns out those so-called details were actually massive cracks in the very foundation of physics. There were these strange experimental results that just refused to fit into this neat, tidy picture of the universe they had built.
So, this solved universe, it really rested on two gigantic pillars. These were powerful, elegant theories that seemed to describe everything, from the way an apple falls from a tree to the orbits of distant planets. First, you had the big one, Isaac Newton's laws of motion and his law of universal gravitation. I mean, this stuff gave us a stunningly accurate clockwork model of the whole cosmos. And then you had James Clerk Maxwell's equations, which just brilliantly unified everything known about electricity and magnetism, and in the process revealed what light actually is.
So the first real crack in this beautiful structure, it showed up when Maxwell's own equations made a prediction about light that was, well, frankly, it was just bizarre.
His math predicted that light travels at one specific, absolute, constant speed. And here's the really weird part. This speed was the same no matter how fast you were moving or how fast the source of the light was moving. It was like a cosmic speed limit that nothing could ever change. This created a huge problem. I mean, for over 200 years, Newton's physics said that speeds are relative. They just add up. It's common sense, right? Like throwing a ball from a moving train. But Maxwell's equations insisted that for light, that common sense rule was just plain wrong. The two pillars of physics were saying completely opposite things.
So what do? Faced with this massive contradiction, a young patent clerk named Albert Einstein made an incredibly bold choice. In 1905, he didn't try to tweak Maxwell's equations. No. Instead, he said, what if Maxwell's right? What if our basic, fundamental ideas about space and time themselves are what's wrong?
And that led him to his theory of special relativity. It's built on two ideas that sound deceptively simple. First, the laws of physics work the same for everybody who's moving at a constant speed. And second, the speed of light is the same for everybody, period. Now, if you just accept those two ideas as true, the consequences are absolutely wild. It means moving clocks have to tick slower than stationary ones. It means moving objects have to physically shrink in their direction of motion. And maybe most profoundly, it means space and time aren't separate things anymore. They're woven together into this single, flexible fabric we call space-time. Okay, so while Einstein is completely rewriting our definitions of space and time, another equally confusing puzzle was popping up, from something as simple as a glowing hot piece of metal. See, according to classical physics, all the established laws of the day, any hot object should be radiating energy. But the theory predicted that as the wavelengths of that energy got shorter and shorter into the ultraviolet part of the spectrum, the amount of energy it gave off should just skyrocket, all the way to infinity. But obviously, that's not what happens. If the old theory were right, every single campfire and light bulb would be blasting out infinitely powerful, deadly ultraviolet rays. This massive, glaring failure of the theory got a fitting name, the ultraviolet catastrophe. And the clue to solving this whole catastrophe actually came from yet another puzzle. A strange phenomenon called the photoelectric effect, which also stubbornly refused to make any sense under the old rules. So check this out. Experiments showed that if you shine ultraviolet light on a metal plate, even really dim UV light, it immediately starts kicking electrons off the surface. But if you shine a super bright red light on it, nothing. Absolutely nothing happens. It was the color or the frequency of the light that mattered, not how bright it was. And that just made no sense if you thought of light as a wave. And who swoops in to solve it? You guessed it, Einstein, in another one of his papers from that same miracle year of 1905. He proposed this radical idea. What if light energy doesn't come as a continuous wave, but in these little discrete particle-like packets? He called them quanta of light. We call them photons. This explained everything perfectly. A single photon of high-frequency UV light has enough of a punch to knock an electron clean out. But a photon of low-frequency red light, it's just too weak. You can blast the metal with billions and billions of them, but it's like trying to knock over a bowling pin by throwing ping pong balls at it. None of them individually has enough oomph to get the job done. So these two solutions, relativity and these energy quanta, They didn't just patch up the old physics. They completely blew it apart. They shattered that old clockwork universe and gave birth to the strange, weird, probabilistic world of modern physics. And at the heart of this new reality is a concept that just, well, it kind of breaks your brain. It's called wave-particle duality. It means that things like light and even electrons aren't strictly particles or strictly waves. They're somehow both at the same time. And they only decide which one to be when we actually try to measure them. So just think about how total this shift was. Where classical physics saw space and time as this absolute, fixed stage for everything to happen on, modern physics sees a flexible, interwoven fabric. Where energy was once this smooth, continuous flow, we now know it comes in little packets. And the biggest change of all? That predictable, clockwork universe was gone, replaced by one that is fundamentally based on probability and uncertainty. Now, you might be thinking, okay, this is some pretty wild, out there stuff. Why does it matter? Well, the thing is, these bizarre, counterintuitive ideas aren't just for textbooks. They are the absolute bedrock of our modern world. Without understanding relativity and quantum mechanics, we wouldn't have semiconductors, lasers, nuclear power, or even the GPS that's probably in your pocket right now. In this whole journey, from a universe that we thought was solved to one of relativity and quantum weirdness, it really leaves us with a fascinating, kind of humbling final thought. The two biggest pillars of physics at the end of the 19th century were built on ideas that just felt right, but turned out to be wrong at the extremes. It just makes you wonder, doesn't it? What fundamental assumptions are we making today that a future generation is going to look back on and smile? And that's really the beauty of physics. Every answer just uncovers deeper and even more exciting questions.